Today. Okay, so today we are cryptography, more cryptography today. What I'm trying to do is take you through a tour of various cryptographic building blocks. And then most uses of crypto that you need, you're going to be able to solve by putting together the building blocks that we're showing you in this course. Okay, so this is kind of like teaching you the different kind of Lego bricks that you can build stuff out of. And project 2, you're going to get a chance to put all these tools to use. You're going to build a version of like Dropbox, like a sharing site, but one that is secure, so that Dropbox doesn't get to see your files. And even if Dropbox gets hacked, they still can't see any of your data. Okay. So what I want to show you today is 2 tools that are used for integrity. And what we looked at last week, in last week's lecture, we looked at block ciphers, which were a method for encryption, symmetric key encryption. In other words, a way of providing confidentiality. Folks on Zoom, you want to just let me know if you can hear okay?
All good.
Yes. Okay. Thank you. Wow. Okay. All right. Thank you. Appreciate it. We just got startled because that was fairly loud here. Okay, good. So we looked at block ciphers and modes of operation. And the crucial thing about them is they provide confidentiality. But as I mentioned at the very end of lecture, they don't provide any integrity or authenticity. Okay? So if you send a message encrypted with a block cipher mode of operation, an attacker, a Mallory, who can modify the encrypted message, might be able to modify it in a way that causes the message that's received to be totally different from what was sent. And the attacker might even be able to make like controlled, predictable changes to the message. So today we're going to build up some tools for solving that problem. And there's 2 building blocks that I want to show you: hashing, hash functions, and message authentication codes. And then I'm going to show you authenticated encryption, which builds on some of those building blocks. So let me start with cryptographic hash functions. I don't really know how they got this name, but a hash function, it's just an algorithm that takes as input some bits, some sequence of bits, and produces a short output that is another sequence of bits, but fixed length. Okay. So given any like file you want, image file, text file, anything, you can use this algorithm to compute the hash of the contents of that file. And what you get back is a fixed length output, like a 256-bit output, no matter how long the input file was. And this function, it's sort of like a hash function in CS61B, 70, where you are like storing stuff in a hash table. If you see the same data item twice, it'll be stored in the same place. You end up with the same hash value. It's like that. It's sort of like a checksum. So it's a deterministic function. If you have a really cute cat picture and you compute the hash of that data, and I have exactly the same cat picture, pixel for pixel identical, and I compute the hash of that, I will end up with the same hash code as you ended up with, provided we use the same hash function. Thank you. Yep. This is going to differ from hash functions you might have seen in data structures, because we're going to look at cryptographic hash functions, which are going to have some additional security properties that are useful for cryptography. And those security properties are going to be one-wayness, collision resistance, and some kind of like randomness or unpredictability, that the output of this hash function is going to look random. Like there's no patterns. It's not going to seem related to the input. If you like make a small change to the input, then it you can't really predict what effect that's going to have on the output without computing the whole hash function. I'm going to talk about each of these security requirements in more detail in a minute. So the idea is the hash function gives this like unique ID or unique fingerprint for a file or a document. Okay, so like each airplane has a little ID number printed on the tail that's different for every airplane. The goal is we want to do something like that in the digital realm instead of the physical realm, so that each file has a different ID. Except that if I have two copies of the same file, like with the same contents, I want them to get the same ID. Okay, so the hash is going to be computed as a deterministic function of the contents of the data in some crazy way. And it's also going to be useful that the output of the hash function, the hash code, is short, even if the input is very long. So for instance, if I have sent you a 1 GB file, and then we want to check whether you received it correctly, whether we've got the same data, I can compute a hash function on my copy of the file. You can compute a hash function on your copy of the file, and then we can exchange the hash code. And if we have the same hash code, then we have the same contents of the file. I don't need to like resend the whole file. We can just check the hash code. Yep. That is it's like an almost guarantee. It's like a cryptographic guarantee. So in other words, for all engineering purposes, it's a guarantee. Someone who could do an exponential amount of computation, could do 2 to the 256 steps of computation, could violate that guarantee, but there's no way anyone can do that much computation. So basically you can more or less treat it as a guarantee. In the same way that like no one's going to be able to guess the AES key that you used for encryption. And we think no one's going to be able to decrypt an AES encrypted message without knowing the key. Same kind of thing here. But is that what you were asking? Okay. Okay, so there's a couple of properties that a cryptographic hash function provides. One of these is one-wayness. Let me tell you what that means. What that means is it's not just that I get a unique ID for each file, but also if I tell you the hash code for my file, you like can't learn the contents of my file. That's maybe not that surprising. And also, you can't construct your own file that has the same contents as that has the same hash code. Okay, so like you can't reconstruct my original file, and you can't like form your own file that like you can't find any file, any input that hashes to that hash code. If I give you a hash code, but I don't tell you anything about my file, you can't come up with a file that hashes to that. That's what one-wayness means. So this is the one-way means like given a file, you can get its hash code, but given the hash code, you can't go backwards. It's like you can turn the cow into a hamburger, but you can't get the hamburger from a hamburger, you can't get back to the cow. So formally, we have a formal definition of this, which is we imagine this experiment where the referee randomly chooses a message or a file X, and then hashes that to get a hash code Y. And then the attacker is an algorithm. The attacker algorithm runs and receives that hash code Y. And its job is to output some X prime, some file or message that hashes to Y. And we're going to count that as a success for the attacker if they output any file that hashes to this hash code Y. So the attacker could output the same X, or it could output some other X prime that has the same hash. Either of those would count as a success for the attacker. And the security requirement of a one-way hash function is that no matter what algorithm the attacker uses, as long as they're limited to some reasonable amount of computation, you know, like all the computation that's possible within a lifetime of Earth or something like that, then they have essentially close to zero chance of successfully winning this game, successfully finding an input whose hash is Y. If I told the attacker X, they could easily find an input whose hash is Y, because X would be an input. But I'm not telling them X, I'm just telling them the hash of X. All right, so like test for understanding. Suppose I define a really stupid hash algorithm that always outputs 42. It doesn't matter what the message is, 42 is your number, is your hash code. Is that function one way according to this definition? How many say yes, it's one way? How many say no, it's not one way? And how many say I'm not sure, I'm kind of shy, or okay, give me a reason for why yes. Why does this, might it seem reasonable to call this one way, or what would be some reasons why this might be thinking yes, this is one way? Yeah.
To the same thing that like since you know the output, you couldn't trace back to the input.
You can't trace back, like seeing the output 42, you can't trace back to the input. It kind of telling you the hash code is 42 reveals nothing about what the input was. So how are you going to be able to reconstruct the input X? Good. Okay. Anyone want to give me a reason, a plausible reason for why you might think no, it's not one way, or at least something that might sound believable? Yeah. Yeah, the attacker who observes, who's given the number 42, can't find X, but they could find another X prime. How would you find another X prime? Any input. Yeah, so it's really easy to violate one-wayness. If I tell you I have a file with hash code 42, you pick any of your files, anything you've got laying around, and that will also have hash code 42. So this is a really stupid hash function, and it's not one way. Right, so correct answer is no, not one way. Okay, another requirement for hash functions is it be collision resistant. So this gets to your question earlier about, can I be guaranteed that if two files have the same hash code, then they have the same contents? That's what collision resistance is getting at. The collision resistance requirement is talking about collisions. So a collision is two inputs that have the same hash code. Two files that if you hash them, yield the same output from the hash function, even though the contents of the files are different. That's called a collision. Collision is bad. Collision is kind of intuitively bad because we wanted to get a unique ID for each file. But if there are collisions, then that means there's two files that get the same ID, even though the files are different. We didn't end up with a unique ID. So a really natural goal for a hash function would be to say no collisions. I want a hash function that has no collisions. There does not exist x prime such that x is different from x prime, but hash of x is the same as hash of x prime. But there's a problem. I could ask for that, but I'm never going to get it. It's impossible to build a hash function that satisfies that requirement. Because if I look at 1000-bit files, there's 2 to the 1000 such files, but there's only 2 to the 256 hash codes. So there's a lot more possible files than there are hash codes. So some pair of files must have the same hash code. That's like pigeonhole principle from CS70. So it means that there's guaranteed to be collisions. For any hash function you pick, there will surely be collisions. So cryptographers actually ask for the next best thing. Okay, collisions are going to exist, but it should be computationally infeasible to find any of them. You can, we'll give you a ton of compute. We'll give you $1 billion in cloud credits on your favorite cloud computing platform. There should be no algorithm you can run that at the end of spending the $1 billion outputs a collision, outputs 2 different files that are different but have the same hash code. Okay, so that's what cryptographic hash functions guarantee. Not that collisions don't exist, but that it's just incredibly exponentially hard to find. And so for all engineering purposes, since no attacker is going to have $1 trillion in compute budget, we can just pretend like you'll never encounter a collision in your life. You don't have to worry about them. So it's as though they had no collisions, though of course they do have collisions. So you can treat the hash code as though it was unique, even though like we know that in some principled way it's not actually. Yeah. Why don't we have the hash enforce? Why not make the hash longer? Yeah. If we made the hash longer, we could avoid collisions. But the problem is, to avoid collisions, the output of the hash function, the hash code, has to be as long as the file or longer. And that's not actually useful. If I exchanged a gigabyte file with you and now I want to check that we got the same, it was received correctly, we have the same data, I don't want to have to resend a gigabyte of data to you again. I want to send something really short. So hash functions were designed to try to be really short to make it really easy to like compare that we have the same file, or to have a unique ID for the file that's really short. Yeah. But you're right, that would be a workable way to avoid collisions. It's just that it's not useful for other reasons usually. Yeah. Assuming there's no weaknesses in the hash function, finding a collision takes exponential time. If you have a 256-bit output, finding a collision should take 2 to the 128 steps of computation. It's half of 256 because of this like birthday paradox stuff. I don't know whether you saw this in CS70, but like if you have 23 people in a room, then it's likely that some pair of them have the same birthday. There's like 365 different birthdays. And if you have about square root of 365 people in a room, there's a good chance that some pair of them have the same birthday. Because if you have n people in a room, if you have k people in a room, there's about k squared pairs. And each pair has about a 1 over 365 chance to have the same birthday. Same deal here. If I hash a whole bunch of messages, then the chances that some pair of them end up with the same hash code, well, if the number of messages I hash is equal to about the square root of the size of the space of hash codes, then it's likely that I will encounter a collision. But 2 to the 128, this is saying if I were to hash 2 to the 128 files, there's a decent chance that some pair of them have the same hash code. There's no way I'm ever going to hash 2 to the 128 files in my lifetime. And probably the human species in its lifetime will not hash a total of 2 to the 128 files. That's a ridiculously large number. So basically, we don't need to worry about it. So there's a bunch of like cryptographers have like designed these things, which we think satisfy all these properties that we want. One-wayness, collision resistance, are really fast, they're deterministic. And it's taken a little while, it's taken a few decades. Some of the early attempts were discovered to be not cryptographically secure. And just so you know about some of the names that you might encounter, MD5 was one of the earliest ones that was invented, and then it was later discovered there are shortcut attacks to break collision resistance, and it's totally insecure, so never use MD5. And then the next one, there was cryptographers came up with an improvement to MD5, which they called SHA-1, and we subsequently discovered that one also has some weaknesses, and so you shouldn't use it today. And so today there's basically two standards, SHA-2 and SHA-3. It's not actually that SHA-3 is better than SHA-2, they're just two different designs, they're both reasonable, use either one, they're both believed to be good. So as far as we know, these are secure cryptographic hash functions. They're one-way, they're collision resistant, their outputs look random or pseudo-random, there's no patterns in the outputs, and they're pretty efficient. There is one semi-weakness or property of SHA-2 that might be undesirable in some settings or might not matter. I'm now in like arcane details. But maybe you need to know it if you're building a system that uses SHA-2, because for some uses this can cause a problem. For some versions of SHA-2, they're vulnerable to what's called a length extension attack. And in a length extension attack, I have a file, and I'm not telling you what the file is. It's a secret file, but I tell you the hash code of the file. You can't figure out what my file is, but you can construct some suffix, m, so that you can then predict what the hash code would be if that suffix was appended to my file. It's kind of weird. It's not clear why this should matter. But there are some situations where it might matter. It's like if you had a way to append that suffix to my file, then you could predict what the new hash code would be. So this could potentially be a hazard for integrity in some like obscure situations. So basically, this is the only known like pattern or regularity or predictability in SHA-2, is this length extension property. Some versions of SHA-2. And SHA-3 doesn't have this. By the way, I should mention as a naming thing, you might see people talk about SHA-256. SHA-256 is another name for SHA-2. All right. So there are off-the-shelf hash functions. You don't want to design one. You want to just use one of them. Okay, so I started out by saying we're trying to solve this integrity problem. So let's kind of look where we got to. Do hashes solve the integrity problem? Encryption does not provide integrity. Do hashes? And the answer is maybe, sort of. It depends on how they're used. Okay, so let me give you one scenario. One scenario could be there's a new version of the Firefox browser out. It's made available on a whole bunch of download servers. And Mozilla wants to enable users to check that the file they downloaded from some third-party server is correct, hasn't been modified, is the correct version of the Firefox browser. Okay, this would enable like caches and download sites to make this download available. People don't have to go directly to Mozilla. Like they could go to, I don't know, a local Berkeley site where you get faster downloads or something like that. So what could Mozilla do to enable users to make sure they got the right file? One thing they could do is they could hash the Firefox download file, the official one, and put that hash code on their website. And they could tell you if you download that from some other third-party download site, after you download it, hash it using SHA-256 and check whether the hash code you get matches what's on the Mozilla website. And if the hash codes match, then because there's no collisions, because, well, it's infeasible to find collisions, that must mean that the copy of the file you downloaded matches exactly the official version. So even though you downloaded it from some website that isn't Mozilla, you were able to verify that the file you downloaded matches what the official version of Mozilla wants you to have. This does require the user to compute this hash and go check it on the Mozilla website. And it requires that the Mozilla website be secure, that no one can like spoof the Mozilla website or like hack what's showing there. So we're just like assuming that anything shown on the Mozilla website is trustworthy. Not very usable mechanism, but you could imagine software doing this for you. And some like software download programs do this. They store files on third-party mirrors, so you can download a copy from a mirror that's near you, that's hosted by a volunteer, and you get a faster download. But security is still assured because they're checking a hash from the original, from the official source to make sure that you're being given like the valid file and not something where there's some malware substitute or something like that. So in this setting, the hash function does provide integrity. But there are other examples where it doesn't provide integrity. There's some scenarios where it's not good enough yet. So let me take another example now. I want to imagine that Alice wants to send a message to Bob over the internet, but the internet is not secure. Maybe it's going over Wi-Fi and someone might be like, someone else might be on the same Wi-Fi network and sending fake radio frequency messages. Might be going through routers on the internet that could have been hacked, or it's going through my landlord's router, and who knows, my landlord might be trying to attack me, or any number of reasons why some attacker might be able to eavesdrop on messages that are sent over the internet and modify messages that were sent. So Alice wants to send Bob a message over this insecure channel. We know how to provide the confidentiality of this message. Alice encrypts the message. But what if we don't care about confidentiality, we want integrity. We want to make sure that Mallory doesn't modify the message. There's nothing secret in it, but we want to make sure that Bob receives the message that Alice sent. A really natural attempt to use hash functions to solve that problem would be for Alice to send a message and also to send the hash function. The hash function, the hash code. And then Bob can check when Bob receives the message. Bob can hash that message and check whether he got the same thing as the hash code that Alice sent. This doesn't work. This is not secure. This is no good. So why is this no good? Why was everything okay in the Firefox example, but this example is not secure? Or what's the security flaw here? Yeah? Yeah. Mallory can modify the message and then also modify the hash code so it matches the modified message. That requires Mallory to know the hash function algorithm, but the standard assumption we're making throughout cryptography is the attackers know what algorithm we're using. There's nothing secret about the algorithm. The SHA-256 algorithm is publicly specified. So this is not secure. The integrity is not protected by this scheme here. Why is this not secure, but the Firefox example was secure? What's the difference? Yeah? Yeah, with the Firefox example, we assume the attacker can't modify what's on the Firefox website, can't modify the hash code from Firefox. But in this example, Mallory can modify everything sent over the internet, including the hash code. So there's no like safe place to start from. Whereas with Firefox, we had a safe place to start from. The contents of the Firefox website are safe. Okay, so hashes on their own aren't enough to solve the integrity problem sometimes, but sometimes not. And the core issue here is that hash functions are a public function that has no key. There's no secret anywhere. So anyone, including the attacker, can compute the hash code for a file, including for the modified file. So that's the problem. Because there's no secret key, Bob has no way to know whether this stuff is coming from Alice or coming from Mallory. So the fix is we're going to next introduce something that's like a hash function, but has a secret key. If it did depend on a secret key, this problem would be solved, because only Alice would be able to compute the hash with the correct secret key, and Mallory wouldn't know the secret key, so wouldn't be able to compute things. So that's the intuition. And for whatever reason, cryptographers have a totally different name for this thing when you want a secret key. And it's called a message authentication code. But if you wanted to think of it as kind of like a hash function, but it's also got a secret key, not a bad intuition. Okay, so let me tell you about message authentication codes. Before I do, any questions so far? Okay. So message authentication codes are designed to solve this problem that we just saw with hashes and the problem with encryption, that we don't yet have a way for Bob to verify who sent the message and to verify that it wasn't modified while it was in transit. So we're talking about symmetric key cryptography. So we can assume that Alice and Bob have a secret key that's been shared in advance. And we want to provide a solution for them now for the integrity problem. And the strategy here is we're going to attach some additional pieces of information to the message to prove that Alice sent this message. Specifically, we're going to have some additional information that can only be computed by someone who knows the key. So we're going to have something like a hash function or a checksum, but it depends on both the message and the key. And only someone who knows the secret key is going to be able to compute the correct value for that. So when Bob receives that, Bob's going to be able to say, oh, it could only come from someone who knows the secret key. The only other person in the world who knows the secret key is Alice. So therefore, this must have come from Alice and not Mallory. That's going to be the strategy. Okay, so the picture looks something like this. This wants to send this message, but with integrity. So she has the secret key. She applies this MAC algorithm, message authentication code algorithm, to compute a value. It's called a tag, but it's just like a hash code or like a checksum. And this tag both the message and the secret key. And then Alice sends both the message and also sends the tag, like appends the tag to the end of the message, sends both of those to Bob. And then what Bob can do, Bob can check the integrity of the message to make sure it hasn't been modified or tampered with and make sure that it came from Alice by using the key, same key, Bob also knows the same key, to recompute the correct tag for this message and checking to make sure that what was sent matches what Bob computed for that message. And if they match, then Bob knows this could only have been computed by someone who knew the key. So someone who knew the key, the only one who could have generated the combination of message and tag is someone who knew the key. And the only other person who could do that is Alice. Okay. So formally, we have a MAC algorithm. Usually it's actually multiple algorithms, one way to generate a random key, a secret key, and then another one, given a key and a message, generates the tag. And the tag you can think of as like a key checksum, and it's short and fixed length. We want it to be short so that we have to append it to the message. So it's like making our using up more data. And so we want it to be short, so we're not need to send too much more data. So that it doesn't like slow down, not too much of a slowdown for Alice and Bob. These algorithms are deterministic. It needs to be deterministic because Alice computes the tag for a particular message. Bob, given that message, recomputes the tag, and they checks to see whether what Alice sent matches what Bob recomputed. So they have to both end up with the same value, so they're deterministic. It's usually very efficient. And there is a formal mathematical definition of what is required for this to count as secure.
Like Alice, where I guess Bob is Alice, that Alice knows.
Yeah.
Bob wouldn't know that same, right? Are we still assuming
We have to assume they met up and they shared secret key. So they and Bob know the secret key. Yeah. So Bob checks that the tag is correct. A more precise statement would be to say Bob knows this came from someone who knew the key. So it must have been sent either by Alice or Bob. Those are the only two people who know the key. And then Bob knows he didn't send it. So the only other option is Alice must have sent it. Are there two individual keys? We'll come back to this and talk about key reuse, but yes, use one key for encryption and a separate key for message authentication. So if Alice and Bob met up in advance, they would agree on one key for encryption and another key for the message authentication code. Yep. Tag means it's like hash code. It's like appended to the message. It's like a checksum. Fixed length means it might be 128 bits long, maybe. The output is the message plus the tag. The message followed by the tag. Both. Bob needs both of them. Yep. Plain text. Right now, we're focusing on integrity only. There's no confidentiality. I'm trying to like separate out confidentiality from integrity. So if you want just confidentiality but no integrity, you can use encryption. If you want just integrity but you don't need confidentiality, there's nothing secret, you can use a message authentication code. If you need both confidentiality and integrity, big surprise, you're going to use both encryption and a message authentication code. So if you look at what's sent here, what's sent is Alice sends the message plus the tag. So any eavesdropper can just observe the message. This is like the plain text. There's no encryption here. So there's no confidentiality provided by the message authentication code. An eavesdropper could directly learn what message is being sent. So if you needed confidentiality, you'd like to also need to do some encryption. The message authentication code won't take care of that for you. Yeah? Is this vulnerable if you use the same key again? Haha. That's what we're going to get to with this formal definition. The basic notion of what it means for a tag to be, a message authentication code to be secure. Well, why don't you tell me? What would be the criteria for a message authentication code to be secure? Given how we're going to use it here, what property do you want from it to make sure that it's going to be good enough for providing integrity? Any thoughts about how you might state that or what you'd be looking for? Yeah?
The attacker should not be
Able to change the message to something with the same tag. Okay, good. So an attacker who doesn't know the key, if they're given a message and a tag, should not be able to compute a new message M prime that has the same tag. That's good. Is that enough? What are you thinking? Have to have a large search space. The key is going to have to be large enough the attacker can't brute force it. And so is the tag. If I had a 1-bit tag, the attacker could send a message and a bogus message and fill in the tag with a random bit, and they'd have the 50-50 chance of it passing verification. So 1-bit tag is not enough. So that's why we use a tag like maybe 128 bits, long enough that it's unlikely that an attacker will guess it just by chance. Okay. Is that enough? We've got now 2 requirements. Yeah?
Can't find, like, can't make a message and a tag that Bob would decrypt to be a valid message.
Oh, good, good, good. That's a stronger version of your requirement. Not just the attacker can't find a way to modify the message and have the same tag, but also the attacker can't find a way to modify the message and predict what the new tag for that modified message would be. Yeah. So if the attacker modifies the message in any way, they should not be able to predict what the tag of the new message, of the modified message is. Good. So I think that subsumes both of your 2 requirements. So that's the basic security notion for a Mac, is if an attacker doesn't know the key, they come up with some message, some bogus message, they shouldn't be able to predict the tag for it. Unless, of course, Alice sent that message and sent that tag, and then the attacker knows what the tag is, but shouldn't be able to do that for any other message that Alice hasn't sent. Is that making sense? How are we doing? Okay, some thumbs up, so I'll proceed. Okay, good. So that's the basic notion of what it means for a message authentication code to be secure. That's what we want. That ensures that an attacker is not going to be able to fool Bob into accepting a message that Alice didn't send. But we actually want something a little bit stronger than that. Cryptographers, ask for the moon because often we get it. So they're going to cryptographers ask for a little more than that. What cryptographers ask for is also it should be secure against chosen plaintext attack. So by chosen plaintext attack, I mean if the attacker can convince Alice to send 10 different messages of the attacker's choice, that shouldn't help the attacker predict a tag on some 11th message that Alice didn't send. So shouldn't be revealing, being able to see a message and a tag should not reveal partial information about the key that lets the attacker eventually reconstruct the whole key or something like that. Okay, so this notion is called existentially unforgeable under chosen plaintext attack. Existentially unforgeable is exactly the requirement that you had, that an attacker can't predict the tag for any message that Alice didn't send. Under chosen plaintext attack means, and that's still true even if the attacker can convince Alice to send some other messages and observe what the tag for them is. So this is going to be formalized by a game. This hypothetical kind of a game where we're going to have two parties. We're going to have Mallory and Alice. Mallory is the attacker. And in this game, Mallory is going to be able to give Alice a whole bunch of messages to send. And Alice is going to send those and apply the correct tag. And then Mallory's going to get to observe what was sent. So that means Mallory can use any message and observe what the tag for that is. Mallory could ask Alice to send the message 1 and 2 and 3 and 4 and 5 and 6 and 7, each single digit number, and observe the tag for each of those. And then eventually, after doing that for a while, Mallory makes whatever inferences she can. Then Mallory chooses some new message that Alice hasn't sent yet, M prime, and tries to predict what the tag will be, makes a prediction at the tag T prime. And if that new message M prime is different from anything that Alice sent so far, and if the predict correct, then Mallory wins the game. She's been able to forge a tag or come up with something that Bob would accept as valid, even though it's actually not. And if Mallory doesn't succeed in predicting the tag value, then Mallory loses. So we imagine running this game. We imagine any algorithm you can think of for Mallory, the most sophisticated algorithm, should be that no matter what algorithm Mallory uses, the probability she wins this game is exponentially small, like 1 over 2 to the 128 or something like that. Tiny, tiny, tiny. So basically, Mallory can't predict the tag on any message that Alice hasn't sent, even under very generous assumptions to Mallory, helping Mallory as much as possible. So that's the notion of existentially unforgeable under chosen plaintext attack, EU CPA. And there are message authentication code algorithms that we believe satisfy this requirement. So they seem very strong. Okay, so then now this can be used to solve the integrity problem. This is exactly the tool we need to ensure that Alice can send a message to Bob and there's no way that an intruder can modify it without being detected. So how do we actually build one of these hash functions? Well, for your purposes, you don't need to design one. There are just some standards, you just go use them. Kind of like SHA-2 is a thing. There are algorithms for message authentication codes. You just grab a library and you use it. But I just thought I would tell you a little bit about how they tend to look internally so you have a little intuition But this is not important. You don't need to know the inner guts of how they work. It's not very important. One way that you can build a message authentication code is called NMAC. And it's a very simple scheme. The dumbest thing you could imagine doing to build a MAC is to say, I'm going to start with a hash function, but I want it to depend on a key too. So I'm going to hash not just the message, but also I'm going to hash the key. So what I'm going to do is take the key, append the message, and hash that whole thing. And that hash code will be the message authentication code tag. That'd be a really naive MAC algorithm. And that'd basically be okay for SHA-3. But for anything that has the length extension attack, it turns out it's not okay. So nobody actually proposes using that. What they do is they do one more step after you hash the key and message. You take that hash code, you combine that with another key, and you hash that. And the output of that, so there's now a two-step process. That final hash code, that is the tag. So that scheme is called NMAC. And there's like mathematical proof that this is EU CPA secure if the underlying hash function is good in some appropriate notion of good. So this is one way that from a hash function, you can build a message authentication code. And it turns out this two-step process prevents an attacker from making use of the length extension vulnerability. That's the only reason you do a two-step process, basically, is because of the length extension vulnerability. So that kind of fixes up that problem. Okay, so it's a very simple scheme. It's about as fast as the underlying hash function. So it's very fast. One thing that's a little bit annoying is I need two keys. And maybe it'd be nice if we had a scheme that used just one key. So there's a tweak, there's a slight modification on NMAC that lets you use just a single key. Alice and Bob only have to agree on a single key. They don't have to agree on two keys. And the trick is we just take our single key and we compute two slight variants of it, and we use that as the two keys for NMAC. And this seems okay, as far as we know. So conceptually, almost the same thing as NMAC. The details don't really matter, but it's called HMAC. And HMAC is one of the standard ways to build a MAC. It's one of the most common, widely used, and it's like an accepted standard, and it's been studied a lot, and it's widely believed to be secure. And I don't care that you know too much about the details. Okay. But I'm just showing you the formula. You can notice some properties here. For instance, it depends on the hash function. You pick any hash function, there's a corresponding HMAC. So you could find a scheme called SHA-2 HMAC, or SHA-256 HMAC, or SHA-3 HMAC. It's just use the scheme, that particular hash function. You can also notice that because the hash function is deterministic, this is deterministic. That's good. That's what we wanted. Intuitively, hash functions produce like unpredictable random looking output. And so the output of this thing will be unpredictable and random looking. That's good. That means we want tags to be unpredictable. An attacker can't just guess what the correct tag might be. So it sort of seems plausible that this would be a reasonable scheme to use. Yeah. Oh, yep. It's a fixed constant. It's just, I have one key, but I really wish I had two. And so I'm going to like modify the key slightly by XORing it with a fixed constant. And the iPad is a single constant byte value repeated over and over, and OPAD is a different byte value repeated over and over. And it's just some like engineering heuristic to try to get, since I need two things for NMAC, to get two things from one. Yeah. How would the length extension work and why is it a problem? How many of you would like to know the answer to that? Okay, let me save that one to see how we're doing on time. I don't feel like I need you to know the details of how that would work, but if we have time, I'll show you how, if we didn't have two hashing steps, if we had just one hashing step, why the length extension property, the length extension attack would mean that this is not secure, not EUFCMA secure. Assume that the attacker can tell.
We don't need to. That's a reason why it's secure.
That's a reason why it'd be unsecure if you had only one key and one hash. Yeah. It's like the length extension attack. Like if I sent a message through the tag and then Mallory appended to my message something that says, oh no, never mind, I changed my mind, actually disregard that, and like the real situation is the following. A length extension attack would potentially allow Mallory to predict how the tag should be modified to make up for that change to the message. Because she's observing. We assume that Mallory can observe the messages transmitted, the eavesdrop on it, and then modify it and send them, make a change. Yeah. Like Mallory controls a router that this message is going through, for instance. Some router got hacked. Yep.
This thing is that they can't implement that. But you said this also applies to like SHA-3, which isn't multiple now.
Yeah.
Why do you have HMAC?
Why not? It can't hurt. It's a little overkill. It's unnecessary. Yeah. Yeah. There's no really good reason. Yeah. If for most of history, all the ways we knew to build fast hash functions had this length extension problem. So we're like, oh, we're going to fix it up by doing HMAC, those two steps. And then SHA-3, people came up with a new way to build a hash function that didn't have this problem, but we were all used to using HMAC by then. So keep using it. I don't know. As I say it out loud, it sounds like a pretty poor reason. All right. So these are authentication codes. Max. Do they provide integrity? Yes. Any modification of the message will be detectable. If Bob detects a modification, in other words, he detects the tag is not correct, then he can ignore the message. Do they provide authenticity? Meaning, can Bob verify message? Basically, yes. But with like a little bit of a footnote or a caveat. If there's a whole group of people who know the key, then what Bob can infer is that one of the people in that group must have sent this message, but can't tell who sent it. If we want to know who sent it, usually what we do is Bob has a key that's shared only with Alice. And then if Bob receives this, Bob can know that it must have come from Alice because it could only have been sent by someone who knows the key, meaning only Alice or Bob. If Bob knows that he didn't send it, then like by process of exclusion, therefore it must be Alice who sent this. So if Bob is, communicating with a lot of different people, then he should, and he wants to know who's sending him messages, he wants to be able to verify that, he should have a separate secret key with each person he communicates with. Yep.
Yeah, the secret key, you send it to the length of the message, and then you hash it to, or then you create two keys of the same length as the message by XORing with a constant. You hash those two keys, and then you hash the message with this.
Almost. I'm not super fussed about you knowing, like memorizing or know how to write down what HMAC does. Almost what you said, but it's a little different. It's like I have one key, I create two variants by like XORing with two different constants. And then what I do is I concatenate one of those keys with a message and I hash that. And I get a hash code. And then I concatenate the other key with that hash code and then I hash that. And I get a second hash code, and it's the second hash code that's the tag. So the first step, if I have a really long message, the first step takes a long time because it's a really long message, long time to hash. And then I get a short hash code out of that. The second step is really fast because I'm not hashing a whole long message. It's just a short key and a short hash code. So the second step doesn't really add too much of a slowdown. And there's some situations where it adds security. So that's why we just always do it. All right, so roughly speaking, message authentication codes provide integrity and they provide authenticity. There's this little asterisk about assuming the key is only shared with 2 people, but basically you can assume they provide integrity and authenticity. Do they provide confidentiality? No. They don't provide any confidentiality. First of all, in this scenario we saw, the message is sent in the clear, so an eavesdropper could just see the key. See the message. Appending a tag does nothing to hide the message. But second of all, the MAC tag is a deterministic function of the message. So by sending the MAC tag, you're somehow violating NCPA confidentiality. Remember how deterministic encryption algorithms were a problem? Because if I sent the same letter twice, I don't tell that both ciphertexts correspond to the same one-letter message. But now if there's a MAC tag present, I could have a problem because sending the same one-letter message twice will end up with the same MAC tag both times, which reveals that both messages were the same. So MACs are not going to provide confidentiality. And there's no guarantee they won't leak partial information about the message. Most ones we use in practice don't, but it's not like a requirement of the definition. So they're a single purpose tool. Okay. So encryption for confidentiality, MAC for integrity and authenticity. And next I want to tell you about what to do if you need both. But is this a good time for a break and stretch our legs? Okay, let's take a 3-minute break, quick break. 3-minute break. All right, break over. That was too short. Back to work. All right, so next I want to show you what to do if you want both confidentiality and integrity. And the answer is that use a tool called authenticated encryption. And we're going to build up this tool from the building blocks we've already seen so far. So we're still in the symmetric key world. We haven't gotten to anything public key. And now we're talking about what if I want both confidentiality and integrity and authentication. And there are schemes out there that are designed to provide all of those. And they're a good default because that's like a good safe stance, is if you're not sure, I want it all. So authenticated encryption scheme is one that provides both confidentiality and integrity. And there's two standard ways of achieving this. One way is to combine a scheme that provides confidentiality. Like what would provide confidentiality? Just yell it out louder because my hearing's bad. Confidentiality. What's a scheme we've seen that would provide confidentiality? Block ciphers, AES, CBC mode, counter mode, something like that. So combine one of those with a scheme that provides integrity. What would be a scheme that provides integrity? Max, HMax, something like that. So you can combine those two. That's one way. The other way is there are people who have designed algorithms specifically for authenticated encryption that kind of provide both all at once, an all-in-one algorithm. And you could use one of those, an off-the-shelf one that cryptographers have designed. Okay. So let's look first at this first strategy of combining these, like some kind of encryption algorithm with some kind of a MAC. And let's look at how we might do that. And I want to invite you to take a moment to think how you might have Alice send a message to Bob by using encryption and a message authentication. Okay, so you can assume that you've got some encryption scheme. Maybe it's AES CBC mode, maybe it's something else. Don't worry about it. You just got an encryption scheme. And you've also got a message authentication code scheme. And you can assume the encryption scheme is secure according to the definitions we've given in this class, indistinguishability under chosen plain text attack. And you can assume that the MAC scheme is secure under the definition we just gave you, existentially unforgeable under chosen message attack. So given those two building blocks, I want you to maybe talk to a partner about how you would use them to send a message. If Alice has a message M to send, what should she send? How should she use these things? What does she send to Bob? Okay, talk to a partner.
That's good.
All right, I want to see what you came up with. I hope this isn't too silly or too basic, but this is the kind of thing that when you're doing crypto systems that you tend to do is like, I have these building blocks, here's what I actually want, how do I combine them? So I'm hoping it's good practice. Hoping you can tell me like what schemes you came up with. I'm curious to see with what you're thinking about how you might use these. What did you come up with? Does anyone want to share? Sure. Can you say it one more time?
Yeah, just think like, could you just encrypt like the message string, then put that to like a message?
Okay, good. Encrypt the message and then put that into the Mac. You want to put the ciphertext into the Mac?
Yeah.
Cool. Put the ciphertext into the Mac. Okay, awesome. Very reasonable. Anyone else? Did you all come up with the same thing? Did anyone else come up with a different suggestion? Any other options? Is there any other option you could do? Is that basically like the only way you could possibly do? Yeah?
Back and then encrypt the message and the code together.
Cool. I could do the Mac first. I could run the Mac on the message. And then what I could encrypt is, I could encrypt just the message, or I could encrypt both the message and the Mac tag.
You want to encrypt both.
Okay, maybe better to encrypt both of them.
Doesn't the mag tag sometimes like
Oh, because a Mac tag might reveal information. Okay, so I think I got at least 3 candidates here, yeah? Any more others?
Yes. Can't you figure out ways for the integrated encryption that's so like the Mac safe?
Ah, so you don't have a good feeling about doing the Mac first and then doing the encryption last. Because like it does feel good there somehow could be used to attack encryption. Because you've already seen something in homework 3? Yeah. Ah. That involves cycling through different variants of the ciphertext and getting Bob to decrypt them and learning something about them. Okay. Did anyone else have any other schemes? Okay. I like your proposal. I like what you're proposing. This is good. So let's analyze them. So I want to analyze them. I want to walk you through a security analysis of each of these 3 possibilities. And I'm going to start with 1. One thing you could do is you could encrypt the message. You could also compute a tag on the message, a MAC tag on the message, and then send both of those separately. Does that make sense? This is sometimes called encrypt and MAC. Because I'm doing them in parallel. Secure? Does this provide confidentiality? Ooh, I'm going to give you a hint and say no. I did the easy part. No, it doesn't provide confidentiality. Now I'm going to ask you to figure out why not. The message is encrypted, right? So why am I saying no? Yeah?
Well, the Mac K2M still is the same problem as Mac, so just that it's.
Mac K2M has the same problem as just macking on its own, which is just deterministic. So there's a leakage here. If Alice sends the same message twice, an eavesdropper can detect that that happened. How would an eavesdropper detect that? Yeah? The MAC tag is the same both times because the MAC tag is deterministic. The ciphertext might be different because there's a different IV, but the tag would be the same. So this actually does not provide the strong notion of confidentiality that we really would like to see. The in CPA notion doesn't meet that notion of confidentiality. I mean, you might argue it's not that terrible because it probably doesn't reveal the message directly, but it does allow to detect repeated messages. So not ideal. Does it provide integrity? If the MAC tag is valid and Bob like accepts this message, must it have been sent by Alice or could it have been tampered with? Yeah? Yeah. You want to say why?
Like if the factor like modify the message, it would need to modify also.
Exactly. If the attacker wanted to modify the message, they'd also have to modify the tag. But we just said that for a secure MAC, that's exactly what's not possible to do. Yeah, totally. Oh, awesome, awesome. So it does provide integrity. So this scheme is a reasonable attempt. It does provide integrity, but confidentiality not really where I want to be. So don't use encrypt and MAC. Next attempt. Let's consider what happens if we encrypt first, and then we apply a MAC on the resulted encryption, what you suggested. Let's analyze this one. I like that suggestion. Does this provide, I don't know, start with integrity. Does this provide integrity? All right, how many say yes, it provides integrity? And how many say no, it doesn't provide integrity? All right, a few yeses. To those who yes is correct, do those who got yes want to help out the rest of the folks in the class to understand why? Yeah? It's kind of the same as the first one because the MAC itself is secure. So if the message gets modified, then the attacker won't know how to modify the tag. It's a little tricky though, because what the MAC is being computed on the ciphertext, not on the message. And I really want to know that the message, the final message that Bob ends up with was approved by Alice. So the attacker can't modify the ciphertext. But could they somehow arrange that Bob ends up with an unintended message? The answer is no, because if the ciphertext is correct, then there's only one thing the message could possibly be. Like, decryption doesn't depend on anything else other than the ciphertext. So this makes sure that the ciphertext is correct, and from that it follows that the message must be correct as well. Yep. Is encryption deterministic? No, encryption is not. We have an IV. We have an initialization vector, a random IV that's chosen randomly each time Alice wants to send a message and is like therefore different every time. So if Alice sends a message and then wants to send another message, wants to send the same message a second time, there'll be a different IV, so a different ciphertext. Yeah. Yeah, so it's a many-to-one relationship where there's multiple different ciphertexts that correspond to the same message. But for any ciphertext, there's only one message that it decrypts to. MAC is still deterministic. All of these, always MAC is deterministic. Yeah. So in particular, the thing we're trying to avoid, for example, is that an eavesdropper shouldn't be able to tell if Alice has sent the same message twice or not. And for this scheme, no. Sure enough, an eavesdropper cannot tell if Alice sent the same message twice or not, because even if Alice sends the same message it'll be two different ciphertexts because of the IV and two different MACs. Okay, so you said yes, this provides integrity, and you're correct. It provides integrity. Does it provide confidentiality? Could the first part of the what's sent leak anything about the message M? No, why not? Randomize the inputs, because we assumed the encryption scheme is secure. So it's protecting confidentiality. Could this second part, the MAC tag, leak anything about the message M? No, why not? Yeah? Yeah. Yeah, the tag is computed based on the ciphertext, not on the message. So there's like no message bits that even go into input to the MAC. So there's no way it could leak anything about the message. There's no one who looks at a ciphertext can figure out what the message is, even if they were to like apply a MAC to it first and then try to infer something from that. So yes, this provides confidentiality. And then let's look at one more example, which is you could MAC first. So this last one is often called MAC, then encrypt. We MAC the message first, then we append that to the message, and we encrypt the whole thing, encrypt the combo. All right, so I'll do the analysis for this one to save you some time. Does this provide integrity? Oh yeah, it does. Oh yeah, it does. Yeah. Because after Bob decrypts, Bob gets something that's a message and the message authentication code on it. Only Alice can generate proper values for this. So if Bob receives that, it must have come from Alice. So yeah, it does provide integrity. Does it provide confidentiality? Yeah, because you're encrypting stuff. Encrypt whatever you want. Since everything is encrypted, it certainly provides confidentiality. Okay. So 3 schemes: encrypt and MAC, encrypt then MAC, or MAC then encrypt. And to kind of summarize, encrypt then MAC is what's usually recommended. We saw from our analysis here that encrypt then MAC and MAC then encrypt both looked okay, but encrypt and MAC looked not good. So definitely don't encrypt and MAC. And it turns out that MAC then encrypt is actually not the best choice either, for subtle reasons that are beyond anything I've showed you in this class. One reason is a theoretical shortcoming it has. It turns out it's not good against chosen ciphertext attacks. And in this class, I said, well, for simplicity, let's only focus on chosen plaintext attacks, and I won't try to complicate things with chosen ciphertext attacks. And usually, like, if it's secure for chosen plaintext attacks, we will be okay for chosen ciphertext too. But this is no exception to that. MAC then encrypt turns out is okay against chosen plaintext, but no good against chosen ciphertext attacks. And we didn't talk about chosen ciphertext attacks, so like, no way you could know that, but it just turns out it's not good. So that's a theoretical reason not to use it. And there's also an engineering reason not to use it, which is Bob gets a ciphertext, and he can't verify the MAC tag until he's decrypted. So the first thing Bob has to do is decrypt. And this message, Bob is decrypting this before knowing whether it's authentic or not. So Bob could be decrypting stuff chosen by the attacker, Mallory, and doing stuff with that. And it turns out that that can be a source of implementation bugs. It's not an in principle algorithmic flaw, but depending on how you implement it can enable some attacks because Bob's code might decrypt and then do some checks on the format and then check the MAC code. And that checking process actually might reveal a little bit of information about the message, it turns out. Depending on how you implement it. If you implement it carefully, it's not an issue. But if you're not careful enough, there could be like this side channel stuff that's kind of obscure. And so for some of the early software systems used MAC then encrypt, and then they had vulnerabilities because of the side channel stuff. And then cryptographers realized, oh, this is kind of a foot gun. So better just not use that because then you don't have to worry about these kind of like obscure side channel stuff about crazy leakages that could happen before you've checked the MAC tag. So the bottom line is cryptographers say just use encrypt then MAC. That's how you get authenticated encryption. A little note about encrypt then MAC. You'll notice that in these slides, I had two keys, a K1 and a K2. And that's because, a little technical detail, you should not use the same key K for both encryption and for computing the MAC tag. It sounds like it'd be really convenient to do, but it turns out that can mess up security in some cases. That's called key reuse. And cryptographic design principle is just don't do that. If you use a separate key for every purpose, a separate key for every algorithm, you're golden, you're great, you're going to be happy. And if you use the same key for multiple algorithms or multiple purposes, sometimes they can cause some like weird obscure interference with each other that is hard to think about and like, So I don't like to think hard. So if you avoid key reuse, you don't have to think hard. If you do reuse a key, you have to be like a crypto expert and anticipate all the crazy ways that like the stuff that the attacker observes from the ciphertext might help break the MAC, or stuff that in the MAC tag might help break the encryption. If they're separate keys, then they can't interfere with each other. So don't reuse keys for multiple purposes. It's okay to use the same key to encrypt multiple messages or to compute the MAC on multiple messages, but you have one key for encryption and one key for message authentication. And like if I am communicating with Charlie and I'm communicating with Doug, I use one key for communicating with Charlie and one key for communicating with Doug because those are different purposes. Or if I am sending email to Charlie and I'm encrypting files stored on my drive, I use one key for emails with Charlie and a different key for encrypting files on my drive. So that, for instance, like Charlie isn't able to decrypt files on my hard drive. Okay. So just don't reuse keys, and then that will take away a class of flaws. And you'll run into this in project 2. That's why I'm bringing this up. You'll like discover, oh, I want to encrypt all sorts of different kind of data. Maybe I have some like file names, and then also the contents of the file, and then also some information about who this is shared with, and maybe those are going to be encrypted, or maybe there's going to be a message authentication code. Can I use the same key for all of those, or do I use a different key for each of those? When is that okay? When is it not okay? You get to think about that in project 2. So an example of this like subtle flaw with MAC then encrypt is an attack on when you go to a HTTPS website, an attack on the algorithm that's used there. And for a long time, that used MAC then encrypt, and everyone believed it was fine based on the reasoning we gave in class. You know, preserves confidentiality, preserves integrity. But then it was discovered that many implementations were vulnerable. And web servers that were protected with HTTPS, it was possible to like decrypt encrypted messages sent to them by this obscure attack. It's like crazy stuff. It's hard to believe that this could possibly enable decrypting messages. But it turns out that this process of checking whether the MAC is correct, recompute the MAC and verify whether the recomputed value equals the received value, that could take a different amount of time to finish, depending on how close it is to correct. If the first byte is wrong, then you immediately know it was incorrect and it can return immediately. If it's correct in the first 15 bytes, but the 16th byte is long, it takes a little bit longer before the comparison discovers that they are different. So there's some timing dependent, there's some stuff that's like data dependent where the time it takes to discover that this is not a valid message depends on the contents of like the MAC tag and how close it was to correct, or the contents of the message. And an attacker who's malicious could send a maliciously chosen ciphertext to the web server. It's not going to be accepted. It's not going to have a correct MAC tag. So it's going to be rejected, but it might take longer or shorter to be rejected. And the attacker can observe when they send the message how long it takes for the server to send back something saying that I refuse, that was invalid. And depending on that timing, they learn a teeny bit of information about the decryption of their chosen ciphertext. And that like 1 bit signal, like took longer or took shorter, if the attacker repeats many times and does some clever stuff, is enough for an attacker who eavesdropped on a ciphertext encrypted in this way to figure out what the corresponding message must have been. Hard to believe that should be possible. But so this like seemingly very minor information leakage due to the timing differences was enough to defeat the security of secure web traffic. So the fix was, use encrypt then MAC, because then the very first thing the web server does is check whether the MAC is valid. And so if an attacker is sending malicious stuff to the web server, the very first check is the MAC valid? And the answer is going to be no, it's not valid, before any non-trivial processing is done. So there's nothing to leak. Timing differences don't leak anything. We don't decrypt or use the decryption key until we verified the MAC is valid. And so it eliminates the whole class of these attacks. Okay, so authenticated encryption, we just talked about one way to do it, which is encrypt then MAC. Another way is you can use a dedicated method that's designed to provide both. And this is pretty convenient. Then you don't have to worry about how to combine them. You just use this authenticated encryption mode. And there are off-the-shelf schemes you can use that provide authenticated encryption. And they're a good default anytime you need security and you have a shared key. And actually, a lot of them provide an extra feature as well. They also provide what's called additional data. So it's a single algorithm that lets Alice provide a message and indicate this part is confidential and this part is not confidential. Provides confidentiality only on the first part and integrity on the whole thing. So the additional data is extra stuff that doesn't need to be kept secret, but that should still have its integrity protected. So that's kind of convenient. And it makes it really easy to use. And there's schemes that provide this authenticated encryption, or AEAD, authenticated encryption with additional data. And you can just use an off-the-shelf one. And you don't need to know how that works, because cryptographers came up with some really clever methods to do this. One of them is called GCM mode, AES and GCM mode. It uses AES in this fancy way to like compute the encryption, and then while it's doing that, also compute the message authentication code at the same time too. So it's also faster because it's computing both at the same time. It's like 2 times as fast. Doesn't matter. You don't need to know the details. All right. So in summary, on integrity, we got hash functions, which provide a way to get like a fingerprint for a file. We got message authentication codes, or MACs, which provide a way to know who sent the message and to make sure that it hasn't been modified in transit, as long as you have a shared key. And then we've got authenticated encryption, which provides both confidentiality and integrity. And my advice is, if there's any doubt whatsoever, You don't need to use encryption. You don't need to use a Mac. Use authenticated encryption for everything. And if you're using authenticated encryption for everything that needs to be protected, you've got both confidentiality and integrity, and you're golden. So all that stuff I taught you about how encryption algorithms work and how message authentication algorithms work, maybe you didn't actually need to know that. Maybe you just need to know use an authenticated encryption mode, and I'm done. Okay, so I am now wrapping up the module on symmetric key cryptography where there's a shared key. And now I'm going to come back to one of the remaining limitations of symmetric key cryptography. And the main one is we need to share a key, which is really annoying. It's really annoying in practice. Like there's no way I'm getting together with you in a coffee shop to like agree on a key just so we can send secure messages. So what I'm going to describe next today is how to solve that problem. Okay, so I'm going to show you some schemes that can be used to securely generate these shared keys, to generate random values, like generate random keys, and then also ways that Alice and Bob can share a symmetric key, but without having to get together in person. All right, so that's what's up. Let's take a break. I got snacks. Take a 5-minute break, and we'll come back in 5 minutes. All right, let's get started again. So I'm going to start with how do you generate random numbers, since we need random numbers for many purposes in cryptography, including choosing a random key. And there's a tool that you can use for this purpose called pseudorandom number generators. Okay. So there are lots of algorithms in cryptography that ask you to generate a random number. Pick a random key, pick a random initialization vector, pick a random nonce. Where do those random numbers come from? Well, one way is you could somehow generate truly random numbers. Like if you flip a coin multiple times, you flip a coin each time you get another bit, do 128 times, and you got a 128-bit random value. But that's really tedious. So we're going to construct some building blocks that allow a computer to generate lots of random numbers very efficiently at very low cost. And by random in cryptography, what I usually mean is like it's not just random, but it's also unpredictable. Like a random key, a random 256-bit key, that should be chosen uniformly at random from all the 2 to the 256 possibilities. So therefore unpredictable because there's so many possibilities. And one concept that's like sometimes useful in cryptography is the notion of entropy, which is a measure of how unpredictable a random value is. And if I flip a fair coin 256 times, I get a 256-bit string. That's considered to have 256 bits of entropy, meaning you would have to predict all 256 coin flips. Or there's like 2 to the 256 possibilities that you're trying to guess among. And there's a formal, precise definition of entropy, but you don't really need to worry about it. Just the intuition is enough. So if you had to guess, if I said I'm rolling a 10-sided die to get a digit from 1 to 10, and then you had to guess that number and how many bits of entropy are there in that random number, it's like a little bit more than 3 bits. Because if I flipped a coin 3 times, that'd be 3 bits. There's 8 possibilities for what the outcomes if I flip a coin 3 times. So like 8 possible outcomes, all equally likely, 3 bits of entropy. 10 possible outcomes, a little bit more than 3 bits. So if I have 2 to the k possible outcomes, all equally likely, that's k bits of entropy. And cryptography generally requires that your secret key and other random values be chosen like in a like true random way, or at least unpredictable, or at least has a lot of entropy. If the algorithm says generate the key randomly, but you actually like use a password, that's not random. Not all values are equally likely. Things that are like a English word or a birth date or something like that are more likely than other possibilities. Some possibilities are more likely than others. And if I choose a value for my secret key where there's too few possibilities, doesn't have enough entropy, then that might enable a brute force attack where someone enumerates all the possibilities. Like if the protocol tells me to use a random 256-bit key, but actually I use a 3-digit code, there's only 1,000 possibilities for my 3-digit code. So someone could try all 1,000 possibilities for the key and just see which one seems to decrypt in a correct way. Would not be secure. And this can lead to some like really catastrophic vulnerabilities in cryptographic software. Where they're supposed to be using random numbers, they're actually not using something that's fully properly random. Actually, when I started as a grad student, the first project I did together with another PhD student was, well, the predecessor to Firefox, Netscape, had just released a web browser that had a new version that allowed encrypting your email traffic. That's not email, your web traffic, that HTTPS for the first time. Another grad student and I looked to see how that worked, and we discovered that the code that was generating a secret key, supposed to be a random secret key, but actually it was derived from the current time, basically. And there weren't that many possibilities for the current time, so an eavesdropper could just try them all and decrypt messages, and we discovered it would be possible for an eavesdropper to like decrypt and break the security of that. And this mistake just is really easy to make and has been made over and over again. And maybe a kind of a really bad example of that is one Bitcoin wallet where, boy, Bitcoin wallet, really security critical. If I screw something up, maybe someone can steal my money and can steal all my Bitcoin. And they used a private, like a secret key to access the account and encrypt all their Bitcoins. And anyone with access to the key could like get into the account and get access to all the Bitcoins and spend all the Bitcoins. And unfortunately, the secret key they used was generated from a 32-bit value. There's only 2 to the 32 possibilities for a 32-bit value, which is like 4 trillion? Billion. Thank you. 4 billion possibilities. And 4 billion is not that many. It's not that hard to write a loop that loops over all 4 billion possibilities and check which decrypted the wallet. And it was pretty easy for someone to gain access to people's funds in this way. So oops, bad mistake. They were using super strong cryptographic algorithms that satisfied all these really good properties, but a really badly chosen key, which rendered the whole thing insecure. So how do we get good randomness and make sure we don't make these mistakes? Well, one way is to try to get like truly random numbers. And for that, we have to rely on some physical source of random values, like flipping a coin. Computers, the instructions are all deterministic. So computers are actually really bad at getting random numbers. And that means you need some like peripheral or circuit or device on there that can like generate random numbers. Or you need like something that's observing some physical process that is random. So like an extreme version of that is like Cloudflare had this wall of lava lamps and a webcam pointed at it. And then they would like repeatedly take pictures of the lava lamp, and the flow of the goo inside the lava lamp, it moves around randomly. And so the exact pixels in that image evolve in a way that's not predictable. And you could use the hash of that image from the webcam as a source of true random numbers. Not very practical, right? Like fun demo, but illustrates not a very practical way to get random numbers. I'm not setting up a wall of lava lamps, as awesome as that would be, just so that I can have some random numbers for my cryptography. So currently, most CPUs provide built-in hardware circuits that do something like this. You have a special instruction and a special hardware circuit that will generate a random number by measuring some physical process that is noisy, and there's inherent unpredictable noise. So you can call that CPU instruction to get a random number, but also it's kind of slow. You have to wait for this physical process to evolve a little bit and then observe it. So it's kind of slow, or kind of expensive to generate a truly random number. And in cryptography, we want to like send lots of messages really fast. We don't want to slow anything down. We don't like slow, we want fast. So in cryptography, what we usually do is we use a pseudorandom number generator. And a pseudorandom number generator is an algorithm. It's not true random values. It's a deterministic algorithm that generates lots of bits that look like they're truly random. How is that possible if it's a deterministic process? The answer is we start by picking a seed, a small value that is truly random, maybe by calling that CPU instruction. And then that is the input to the pseudorandom number generator. It takes a while to generate that 128-bit seed, but we do that. Then we run the pseudorandom number generator on that input, and it outputs lots of pseudorandom values, like maybe megabytes of data, that each one looks like it was generated from a truly random process. Like it's 50-50, equally likely to be 0 or 1. If you've seen the previous half a megabyte of data, you can't predict the next one. There's no patterns in there. In fact, it's so random looking that if I gave you a megabyte of data and I said, secretly, I either generated a megabyte of true random numbers or I generated a megabyte with a pseudorandom number generator, can you guess which? You won't be able to tell which one it came from. Okay. So their output is like as good as if it were truly random for all that you can tell, assuming the amount of computation power you have is limited to like the lifetime of the known universe or the solar system or something like that, even though it's not actually truly random. That's what a cryptographic pseudorandom number generator gives you. But it is deterministic. It's a deterministic function of this seed, this truly random seed. Usually a pseudorandom number generator comes with at least 2 algorithms. There's an algorithm called seed, where you call that with some truly random numbers, a short string of truly random numbers. And then there's a generate algorithm that generates some pseudorandom data, and you can generate as much pseudorandom data. So you set the seed once, and then you call generate over and over and over again, and you get a whole bunch of pseudorandom values that are all unpredictable. And even if you've seen all the previous outputs of generate, you can't predict what the next output of generate will be. Many pseudorandom number generators also provide an additional functionality called reseed. And reseed says, oh, I just made another observation of this physical process. I've got another truly random number. Why don't you take that into account and like mix that in with everything else that's known, and so that future outputs of this depend on that additional randomness. So this is kind of like a hedge. What if the first seed that I set, I thought it had enough entropy, but it actually didn't, unbeknownst to me. And then later, like once a minute, I call reseed with some additional random numbers. Eventually, I'm going to have enough randomness for all those reseed calls, then I'm going to have enough entropy, and then I'll be okay after them. So a pseudorandom number generator has some initial state. When you set the seed, it like initializes the state. Each time you call generate, it produces some pseudorandom output and updates the state so that it can like be ready to generate more. And usually what we do in practice is we might have multiple sources of true random numbers. Often sources of true random numbers are not very reliable. Like one example of a source of true random numbers is I look at the timing between network packets that I receive during the first minute after boot. It's kind of hard to predict exactly what the timing down to like the microsecond or nanosecond of arrival of those packets will be for anyone else. But maybe no network packets arrive at all, and then there was no randomness in that. And maybe I also use the CPU instruction, and maybe I use some other sources. And so ideally, I want something whereas at least one of those had some entropy in them. Then I will end up with I will be safe. So often, what people do is they generate true random values from multiple sources or multiple physical processes, and they mix them together by calling seed and reseed multiple times with data from different sources. All right, so we're going to try to construct a PRNG, and let me give you a definition of what I mean by a PRNG to be secure. Well, first of all, I'll note that the output from a PRNG is not truly random. Usually we have a short seed, like maybe a 128-bit seed. Maybe that's all I can afford to generate in a reasonable amount of time with my CPU's instruction. But I might want to generate a megabyte of data. So can all possible 1 megabyte sequences be equally likely? No way. There's only 2 to the 128 possible seeds. So there's only 2 to the 128 possible outputs. And all the others are impossible. So the output from a PRNG can't be truly random. Can't have the same distribution as if I'd flipped a coin 8 million times. But what we're going to demand is that no attacker who has a limited amount of computation time, like $1 trillion of cloud computation credits, should be able to detect any patterns that indicate a deviation from what you would expect if this were truly random. Okay, so the formalization involves a game. It involves a game where the attacker is given either a truly random sequence of 8 million bits, or they're given 8 million pseudorandom bits produced by a PRNG that was seeded with a 128-bit truly random seed. And the attacker's goal is to guess whether the data came from true random or from pseudorandom. They can get it right with 50% of the time easily by just blindly guessing. If they can get it right 51% of the time, then we say the pseudorandom number generator is broken. It must be biased in some way. There must be some patterns in the output that would not appear in its true random values. No good. Okay, so the attacker wins if they can guess with slightly better than 50% chance the source of the data. And if the attacker can't, no matter what algorithm they use, they still can't do better than 50%, then we say the pseudorandom number generator is secure. And for engineering purposes, wherever I need random numbers, I could just use pseudorandom numbers, and it'll be as good as that. No one could tell the difference. Can't possibly make any difference to the way I'm using it. If it did make a important difference to the thing that is using those pseudorandom numbers, then that important difference could be used to recognize that the pseudorandom numbers are not truly random and to break the PRNG. It turns out that there's another mathematical definition that happens to be provably equivalent. The other mathematical definition is if we imagine an attacker who sees 7 million bits of output, the first 7 million bits of output, and has to predict the next bit of output from the PRNG. Can they predict it? Well, obviously they can guess right with 50% chance, but if they can do better than 50%, like 51% chance right at predicting an output bit, given all the previous output bits, we consider this to be insecure. That turns out to be equivalent. Every PRNG that's secure under one of those definitions, under the game definition, is secure under the predicts the next bit definition, and vice versa. So another way to think about PRNGs is no attacker can predict the next bit unless they have exponential compute power. Here's a case study from the real world that you don't need to know about, but it's kind of fun. It illustrates what happens if we use a bad PRNG. There's this casino, apparently, in St. Louis that casinos monitor their profit, and started to see they were losing a bunch of money on their slot machines. And so they're like, what the heck is going on? So they stationed some employees, some staff to stand by the slot machines and just watch what's happening. And they noticed that there was a few players who looked kind of sketchy, and they would hold their hand over the lever and then at a very specific time, pull the lever, spin the machine, they play at a very specific time. And they eventually figured out what was going on. The slot machine used a pseudorandom number generator to generate what sequence of cherry and apple and so on would show up at each second. And when you pull the lever, it used whatever was the current one. And if that was 3 cherries, you won money, right? This turned out to be predictable. And so these people built a smartphone app that observed the sequences of stuff showing up on the slot machine, was use that to figure out what the internal values of the PRNG was and to predict all the future outputs. At each second predicted what the output would be if you played right now, and it would tell you when to play because it knows what seconds you would win and what seconds you would lose. Okay, so broken PRNG enabled people to make money off of this casino, basically. And incidentally, I thought it kind of interesting that Vegas casinos were not affected, and Vegas is super highly regulated. They have a gaming commission that that evaluates all slot machines to make sure that they're fair. Their goal is to make sure they're fair to the players, but also it turns out that ensures that they're fair to the casinos too. And those machines didn't get approved in Las Vegas. Another case study of examples of what happens if we use a bad PRNG. There was a very bad vulnerability in Linux software, specifically Debian Linux distribution, which was also used in Ubuntu for SSL, the HTTPS, the encryption used on the web. And the mistake was they had a PRNG that was gathering seed from multiple sources. One source was a 15-bit process ID, and another source was like scavenging around in memory to look at what values were left over from earlier processing. Not a great design. But then it got worse because some maintainer looked at this software and was running it with a debugging tool and noticed that the code was accessing uninitialized memory, and the debugging tool gave them a Valgrind warning message. And they said, oh, that's a bug. This code shouldn't be accessing memory that hasn't been written to. And so they just removed that line of code. They're like, what the heck? And then the software kept working and it no longer gave these warning messages. But what they didn't realize is that this bug fix eliminated one of the sources of entropy. So now the only source of seed material for this PRNG was a 15-bit process ID, which meant there were only 2 to the 15 possible seeds. So there were only 2 to the 15 possible output values. And this was used to generate the private keys for web servers. And so this enabled anyone in the world to figure out the private keys for every web server that was running on Debian and I think Ubuntu. Really, really bad. It was like catastrophic security vulnerability because some developer did something that looked completely innocuous. And the nasty thing about these like random number bugs is if you have a bad quality pseudo-random number generator that's generating output that's predictable, your program still appears to work. It's not like you get an error message when you run the program or the program crashes. Everything seems to work. It's just that it is silently vulnerable. And you'd have no way of knowing unless you like really carefully inspected the code or you're like, you know, a cryptographer, basically. So this bug was sitting around in the code for a while, leaving a whole bunch of people vulnerable. Okay, so tricky stuff. Another feature that some pseudorandom number generators provide is a way to recover from compromise. If your machine gets hacked, then the hacker might run GDB and extract the current state stored by the pseudorandom number generator. And then let's suppose the hacker loses access to your machine, you reboot or something like that. Can they predict future values from the pseudorandom number generator? And with many pseudorandom number generators, the attacker can, unless you reseed. And so very secure systems will once an hour, once a day, reseed, meaning pick a new seed, new truly random seed, and like combine that into the state of the pseudorandom number generator so that just in case the old state of the pseudorandom number generator got revealed to the attacker, that'll be enough to predict future values of the pseudorandom number generator until you reseed, until you mix in more truly random values. So there are a whole bunch of pseudorandom number generators schemes, but a very simple one you can use, and will give you a good intuition about how pseudorandom number generators work, is AES encounter mode. Okay, so you take the seed and you call that the key for AES. So the key to AES is the seed that was provided. And then you run AES encounter mode to generate a pad. Or equivalently, you encrypt the all zeros message. And that will enable you to generate lots and lots and lots of output bits. To get the first 128 bits, you encrypt a counter where the counter is set to 1, and then you increment the counter to 2, and you get another 128 bits, and you increment the counter to 3, and you get another 128 bits. And you just keep streaming and get as much output as you want. And you use that output as the output of the pseudorandom number generator. Because the outputs from block ciphers are like random looking and unpredictable, you get a stream of bits that, to someone who doesn't know the key, look random and unpredictable. But to someone who does know the key, or the seed in this case, it's a deterministic function of the seed. Yeah. Yes. Yep. It's one seed. So you use that to generate, that one seed to generate as much output as possible. So the key is the seed, so same key for all the blocks. Yep. This is a way you can get a pseudorandom generator that doesn't have the capability to reseed. This is just you set one seed and then you're done with it. That's what you use forever. Yep. What do you put in the plain text? You just use the pad from counter mode, or if you prefer, you can set the plain text to be all zeros. And there are other schemes, and you can look on the slides to see another scheme here that's built using HMAC as a building block. And you can use that to build a pseudorandom number generator that lets you reseed, lets you mix in more true random values periodically. And I'll just let you look through the algorithm on the slides. It's not too hard. You have some internal state values, and at each step, what you do is you update those internal state values using HMAC. And then you can use that to generate output. The output of HMAC on the internal values is an output. And you can mix in new true random numbers by including them in the input to HMAC, and then update the state based on that. And then this gives a stronger property of allowing you to reseed and giving you rollback resistance. So once, if you reseed with new true random numbers, even someone who somehow managed to learn the old state secrets for the old seed for the pseudorandom number generator can't predict any outputs after the reseed. Another case study in bad pseudorandom number generators. There was a programming framework that for web applications that provided some support for enabling people to reset their password if they forget it by sending you a reset link to your email. And how does that reset link work? They pick a random number, random, so it'll be unpredictable to an attacker, and email you a link, a URL containing that random number. And then when you come to that website with that random number, they know it must be coming from someone who could read that email, so they can let you change your password. And the flaw in this was they used a bad pseudorandom number generator, one that was not cryptographically strong. And so I could press reset, do the password reset like 5 times, and observe 5 outputs from the pseudorandom number generator, because I get 5 emails with 5 links containing 5 pseudorandom numbers. There are sequential outputs from the pseudorandom number generator. And then it was possible from that to figure out the entire state of the pseudorandom number generator and predict all future pseudorandom numbers that would be output by the pseudorandom number generator. So I could start by entering my email address in and clicking send me a reset link 5 times. It comes to my email address. And then I would enter in your email address and say send a reset link. And that reset link would go to your email. I can't see it because I can't read your email, but I can predict the next pseudorandom number from the pseudorandom number generator because of the flaw. And so that enables me to go to the website, to the URL with that predicted next number, and the website thinks it's you. And let me set your password to a new password. So this would have been secure if they'd used true random numbers or a cryptographic strength pseudo-random number generator, but because they didn't, it enabled stealing other people's accounts. You will discover in the project that it might be useful to be able to identify different objects with a unique identifier. And the common way to do that is to use what's called a UUID, like a 128-bit value that is unique. Every object, every like different file has its own unique UUID. And one way to get unique values to ensure they're unique. See, how do I ensure that my UUID is globally unique? There's no one else in the world who has the same UUID as what I'm using for this new file I just created. I could have a counter, but my counter, maybe I have a counter and you have a counter, and our counters might overlap and end up with the same value. And then you have a file and I have a file and we have the same UUID even though they're different files. Yuck, that's no good. So a standard way to ensure that the UUID that I have is different from every other UUID in the world that anybody else has for any of their files is I generate a random 128-bit value. And then it's very unlikely to match any of the other UUIDs that anyone else is using. Okay, so PRNGs are a fast way to get random values, basically. Stream ciphers, another way to encrypt with symmetric key encryption. And we don't need to know too much about this, but basically it's an alternative. It's like a generalization of AES counter mode. Remember in AES counter mode, the way that worked was use the key to generate this pad. There's a pseudo-random pad, and then XOR the message with the pad. So a stream cipher is just a generalization of that. A stream cipher is a method to generate a pad from the key. And then the way we use a stream cipher to encrypt the message is we generate a pad as long as the message, and we XOR bitwise between the message and the pad. Like the one-time pad, except our pad's not truly random, it's generated with a stream cipher. And what we need for a stream cipher to be secure is for the bits of the pad to be pseudo-random. So there's a very close connection between pseudo-random number generators and stream ciphers. One way to build a stream cipher is to use a pseudo-random number generator, where you take the key that Alice and Bob have shared, and you treat that as a seed to a pseudo-random number generator, and you run the pseudo-random number generator to generate this pad, generate pseudo-random bits that will be considered the pad. And Alice can do that starting with the key as the seed, and Bob can do that starting with the key as the seed, since both Alice and Bob know the key. Because pseudo-random number generators are deterministic, they will both end up with the same pad. So Alice can encrypt by XORing her message with the pad, and then Bob can decrypt by XORing again with the same pad. Okay, so when we talked about AES counter mode as a way to encrypt, or AES counter mode as a way to build a PRNG, like same thing. That's why we could have this same tool used both for encryption or for building a PRNG. If you have a stream cipher, you can use that as a PRNG. If you have a PRNG, you can use it as a stream cipher. They're very closely connected. Now, the tricky bit is you can never reuse a pad, right? With a one-time pad, if I encrypt two messages with the same pad, no bueno. Not secure. So if I'm going to do a stream cipher, there's a problem with this scheme that I just described. What if I want to encrypt one message and then I want to encrypt the second message? I can generate a pad for the first message from the PRNG, but how do I get a pad for the second message? I don't want to reuse the same pad. So I need a way to actually generate not just one pad, but multiple pads, a separate pad for each message I want to encrypt. In other words, get different pseudorandom number bits for each message, even though it's the same key for all of them. If you have a pseudorandom number generator, one way is to take the key and the initialization vector, concatenate them, and use that as the seed. So now, each time I encrypt a message, I have a different IV, and I get a different set of pseudorandom bits for the pad, and it's a secure way to encrypt. Okay, so if you look at it one way, you can see AES counter mode is a type of stream cipher, because the output is pseudorandom and it's exclusive word against the message. If you look at it another way, you can see it as a type of pseudorandom number generator. The key is the seed, and it outputs pseudorandom bits as a function of the key. The nice thing about stream ciphers is that they can encrypt data in a streaming fashion. You don't have to wait for the entire plain text to be finished before you can start encrypting. As each bit of plain text becomes available, you can encrypt it because you're doing bit by bit XOR and immediately send it. So that's why they're called stream ciphers, because it allows streaming processing of like data that's continuously arriving. Okay, but basically stream ciphers are just another form of symmetric key encryption. They're just another alternative to like AES CBC mode encryption. You can, for most purposes, you can use either one. All right, so that's enough on symmetric key cryptography. What I want to talk about next, the key assumption behind symmetric key cryptography is that Alice and Bob have shared a key. They have the same key. And I want to talk about how they end up with the same key, how they share a key. But before we do that, I think now is a good time to take a 3-minute break. So a little stretch break, stroll around, and then we'll come back in 3 minutes and we'll talk about how to share a key. Okay. Diffie-Hellman key exchange. This is how we're going to share keys, or at least one way to share keys. This is sweet. We get to use some CS70 stuff now. I'm going to show you this scheme called Diffie-Hellman key exchange, which is a way that you and I could end up with a shared key even if we don't meet in person, just by like phone messages or, you know, something over the internet, just communicating digitally. And it's going to involve some like number theory and modular arithmetic and so on. And I'm going to show you that in a minute. But since like math can be like kind of overwhelming, I want to start with an analogy to give you like some idea about how this works first before we dive into the math. And hopefully it'll give you a little intuition about what the math is trying to achieve. So I want you to imagine that Alice and Bob are trying to come up with a secret color that is known to both Alice and Bob. And they're going to be sending like paint cans to each other. And the mailman might be snooping on the paint cans, observing what colors they send back and forth. And our goal is to come up with a way that Alice and Bob can send some paint cans back and forth so they both end up with a secret color, the same secret color, but the postman can't guess what their secret color is. Sounds weird and maybe not achievable, but surprisingly, it is achievable. And the idea is Alice is going to have her own individual secret color that only she knows, and Bob is going to have his own individual secret that only he knows. Here, Alice's is red and Bob's is that teal? I'm really bad with colors. Teal? Okay. They have a common starting point. There's nothing secret about the starting point. Yellow. Yellow is like everyone knows that they start from yellow. And Alice is going to mix yellow plus her secret color, yellow plus red. And the mixture there is going to be some like orange brownish thing, let's say, and send a can of paint to Bob through the mail with that mixture, that orange brown color. And Bob is going to mix yellow with his secret color, teal. And he's going to get something that's kind of bluish looking. And he's going to send a can of paint with the mixed, you know, that blue color to Alice through the mail. The postman is observing this. So the postman can like pry open the paint cans and look in and see, oh, Alice is sending some brown and Bob is sending some blue. And we're assuming that once you mix paint, you can't like get back what the original colors were. And then Alice is going to take the color, the paint that Bob sent her, this blue, and add her secret color to that, the red to that. And the result might be this ugly green puce thing. Bob is going to take the can of paint that he got from Alice, this funky orangish, brownish, and add his secret color, the teal, to that, and he'll get the same thing. The same thing, puce. So you'll notice that Alice ends up with yellow plus teal plus red. And Bob ends up with yellow plus red plus teal. It doesn't matter what order you mix paint together. They end up with the same color. Because they end up with yellow plus a little bit of Alice's color plus a little bit of Bob's color. So they end up with the same final color, that puce. And now here's the magical part. The claim is that the idea is the postman won't be able to predict that they both end up with puce. Except, is that really true in this example? I'm not convinced it's really true in this example. I think in this example, the postman could figure out that they end up with puce. because a postman could observe blue and be like, what is blue minus yellow? That must be teal. And what is orange minus yellow? That must be red. And therefore, like, figure out what that red and teal were Alice and Bob's secret colors, and like reconstruct that they must end up with puce. But notice that puce was never sent between the two of them. So this is not actually secure. They do end up with a common color, but it's not like hidden from what the postman could probably infer what common color they end up with. But we're going to do some like number theory version of this with some math that's going to do something similar. For a similar reason, they end up with a common color, a common shared key. But the difference with the modular arithmetic is the math is going to make it so that the postman can't predict what that common color is or what the shared key is. Okay. So here's the math. Sorry, we're just diving in now. The math is going to work with modular arithmetic. It's crazy. Like number theory is this thing that like there's this 100 years ago, 150 years ago, mathematicians studied because it's beautiful, and they were sure that it had no applications whatsoever. And then, 80 years later, it turns out, oh my gosh, it has this really important application, enables security on the internet. So who knew? Who could have predicted? But anyway, so we're working with modular arithmetic, and that means that there's going to be a very large prime number, p. And all of the arithmetic we're going to do, addition, multiplication, is done modulo p. So whenever you add or you multiply, you then reduce it modulo p. You take the remainder mod p. And we're going to have a prime that is everyone in the world knows and is fixed. It's the same for everyone. There's nothing secret about it. And also a number g. All our numbers are going to be between like 1 and p minus 1. And so our number g is going to be a number between like 1 and p minus 1. And it's going to be a really big prime. And the scheme relies on this funky notion, the discrete log problem. It's kind of crazy, but there's an operation you can do that's very fast to compute, but seems to be very hard to undo. Okay? So if I know the number g, and I know the prime p, and I know a number a that's an exponent, there's an algorithm I can use to compute g to the 8th power modulo p. And that's like a fast exponentiation or a square and multiply algorithm that I think you might have seen. Did you see this in CS70? Maybe? Maybe not. Okay, well, you can take it on faith that it turns out there is an efficient way to compute g to the a mod p. If you want g squared, you like g times g and then reduce that mod p. And if you want g to the 4th, you first compute g squared and then you square that. And if you want g to the 8th, you first compute g to the 4th and then you square that. You can get, and if I want g to the 12th, I first get g to the 4th and then I get g to the 8th and then I multiply g to the 4th times g to the 8th. And after every multiplication, I reduce mod p so the numbers don't get too big. Okay, so there is an efficient algorithm to compute g to the a mod p from g and p and a. But as far as we can tell, if I tell you what g to the a mod p is, and I don't tell you what a is, so I tell you g to the a, I tell you g, I tell you p, there is no known algorithm to reconstruct what a is. It's believed to be very, very hard to find a. So there's like one direction you can compute efficiently, exponentiation. There's an efficient algorithm for it. But the other direction, computing the logarithm, given g to the a, find a, is believed to be very hard. There's no efficient algorithm known. As far as we know, it takes exponential time to compute that. I have no proof, but cryptographers and mathematicians have studied that problem for a few decades and no one's come up with any efficient algorithm. So assuming we're right that there is no efficient algorithm to solve the discrete log problem, then the scheme I'm going to show you is going to be secure, or that's kind of the basis for the security. Okay, so that's going to be our starting point. We're going to start from this, and that gives us a function that's one way, going from A to G to the A mod P. Can be done efficiently, but going back can't. So that's like cow to hamburger, but you can't go back from hamburger to cow. It gives you a one-way function. And we're going to use that together with this paint mixing idea to get an algorithm that Alice and Bob can use to end up with a shared key. And the idea is, instead of mixing paint, we're going to raise to a power, raise to a secret power. Instead of adding in Alice's secret color, we're going to raise to Alice's secret number A, raise to the power A. And G to the AB is the same number as G to the BA. So just like with paint, you can add in red and then teal, or add in teal and then red, and you end up at the same ending point. You can exponentiate to the 8th power and then the bth power, or exponentiate to the bth power and then the 8th power, and you'll end up with the same number. Okay. So the scheme is like this. Alice generates a secret number, A, that's known only to her. This is like her secret color, red. Bob generates a random number, B, that's known only to him. This is like his secret color, teal. These are numbers between 1 and p-1, let's say. Then Alice does this exponentiation. She computes G to the A mod P. We said that can be done efficiently. Bob does the exponentiation on his secret value. He computes G to the P mod B. That's like, G is like yellow and A is like red. So it's like mixing the base color yellow with Alice's secret color red. And the G to the A is like that mixture, that orange. And Bob does the mixture too. And then they send, Alice sends that number, G to the A mod P, to Bob. And Bob sends that number, G to the B mod P, to Alice. So they send their mixed paints to each other. Alice receives G to the B mod P from Bob, and then she exponentiates with her secret number. So she gets G to the B, then raised to the 8th power. Bob gets G to the A from Alice, and then he exponentiates that with his secret number. So he gets G to the A and then raised to the bth power. And by what we just said, G to the B to the A is the same as G to the A to the B. So they end up with the same final number. That final number is G to the A times B power. They both end up with that number. But Alice never sends her secret number A, and Bob never sends his secret number B. So what does an eavesdropper observe? Can an eavesdropper predict this final number that they both end up with? They end up with a common number, just like they ended up with a common paint color. The difference here is now an eavesdropper or a postman cannot predict the final number they come up with, as far as we know. Because what can the eavesdropper observe? Eve does not get to see A or B. She gets to see G to the A, and she gets to see G to the B. Can she compute G to the A times B from these two numbers? As far as we know, no, there's no way to do that. She could like take G to the A, multiply that by G to the B, but that doesn't give you what you want. That gives you G to the A plus B power, not the A times B power. She could take G to the A and try to figure out what A was, but that's the discrete log problem, which you said that there's no known algorithm for. So there's no known way to back out what A must have been, given what G to the A is. And similarly, there's no known way to back out what B must have been. So as far as we know, there's no way that Eve can predict what final number they end up with. So therefore, after Alice and Bob has finished this process, they can use that final number as like an AES key, as a shared key that is known to both of them, but not known to the eavesdropper. It turns out it does. If you take G to the A, it doesn't factor out of the like the exponent up here, but like if you take G to the A first, mod P, and then to the Bth power mod P, that gives you the same number as G to the B mod P and then to the A mod P. Oh,
But we don't know G, or Bob doesn't know what G to the A. He knows what G to the A.
Bob knows what G to the A is because Alice sent it to him.
Oh, he sent G to the A.
Alice sends G to the A mod P. I'm sorry. Okay, I should warn you. G to the A mod P is a long string of stuff to say. So when sometimes I get sloppy and I say G to the A. And what I really mean is G to the A mod P. Every number that you see, always the first thing I do is I reduce it mod P. In modular arithmetic, if I want to multiply 57 times 61 mod 10, I don't multiply 57 times 61. I'm going to be here all day if I do that. I first reduce 57 mod 10 to get 7 and 61 mod 10 to get 1. And I know the final answer is 7 mod 10. So with modular arithmetic, you want to do some complex calculation. You can first reduce the intermediate values modulo 10 or modulo P. Reduce every intermediate value and replace it with the modulus value, and you'll still get the same answer. Oh, sorry. This is so hard to talk about. Help me out here. If you're lost, help me help you get unstuck. If you're lost, I'm sure you're not the only one. I'm so sure of it. Maybe you want to look on this on your own. Okay, I'm gonna give a little time to and then you can ask questions if I'm not explaining very well. So if we look at the knowledge, what each person knows, Alice knows A because she picked it. She can therefore compute G to the A mod P, and she knows G to the B mod P because Bob sent it to her, but she doesn't know B. Bob knows B because he picked it. He can know G to the A mod P because Alice sent it to him, and he can know G to the B mod P because he can compute it from B, but he doesn't know A. And Eve only knows what was sent, but doesn't know A or B. And it turns out that from what Alice knows is enough to compute G to the AB mod P. And what Bob knows is enough to compute G to the AB mod P. And if the whole mod P thing is really hard to think about, you can just imagine that there's no mod P's anywhere. And then all the algebra looks a lot simpler. You don't need any mod P's anywhere. You can imagine that the final answer is G to the AB. And then it's maybe easier to see that G to the 8th power, that to the Bth power is the same as G to the Bth power, that to the 8th power. And what I'm promising you is that the same thing is true in modular arithmetic. So if I throw in a whole bunch of mod P's everywhere, same kind of facts still hold. Modulo prime turns out to be magical in that a lot of the things we're used to about working with numbers also are true when you work with modular numbers. Yep.
They just communicate.
Aha, how do they decide on G and P? They could communicate insecurely. Alice could just pick it and tell Bob what to use. Or another method that's often used, that's one method that's often used. Another method that's often used is there's some standard somewhere There's an RFC, a standards document that says, if you want to do Diffie-Hellman, use this G and use this P. This is the thing for everyone in the world to use. That works too. You would think it might help the attackers, but the attackers, because the attacker knows G and P. But here's the magical thing. Even when the attacker knows G and P, still, we haven't figured out any way that that would help an attacker. Like we tried all these number theory ideas and none of them seem to help an attacker predict the final value. Kind of mysterious why that should be, but it's kind of related to this discrete log issue that we know how to exponentiate, but we don't know from G to the A how to get back to A. And that's a way that modular arithmetic is different from normal numbers. Normal numbers, they're efficient algorithms to exponentiate and to compute logs, but for this modular arithmetic messes that up. And I have like a visualization of what like, if we, in normal numbers, if we plotted G to the A as a function of A, you get the right curve and it's a smooth curve. It's a nice smooth curve and smooth curves are nice and you can undo that function, you can find the inverse. But with modular arithmetic, if you plot the curve of G to the A mod P as a function of A, it jumps all around. It starts going up, but then it wraps around back down, and then it's going up, but then it wraps around back down, and it goes up, and it wraps around as fast as it goes up. And so like it's going up as much as it's going down, and there's no longer any smooth looking pattern there. And so that's why we intuitively, we don't know any way to compute the inverse of this function, given G to the A back out A. In this function over here, if I gave you G to the A, I told you where you are on the y-axis, you could easily back out where X is by like doing binary search or something. Here, there's no such like regularity that would make it easy to back out what it is. Okay, so this is Diffie-Hellman key exchange. This can be used to generate a shared key whenever Alice and Bob want to use symmetric key cryptography. So anytime that Alice wants to send a message to Bob, she can send a message to Bob saying, hey, let's do a Diffie-Hellman so we have a shared key. We don't have one yet, but let's do it. And then they send this stuff back and forth, and now they have a shared key. And then Alice is like, okay, good, we got a shared key. Now I'm encrypting my message with that shared key, and I'm sending you the ciphertext. So anytime they want to communicate, they can do a Diffie-Hellman exchange. That key might be known as a session key because it's used for one message or one brief interaction or one session. This is sometimes called ephemeral Diffie-Hellman, DHE. And the ephemeral part is if today I want to send a message to Zelda, I do a Diffie-Hellman and then I send a message. Maybe she sends me a reply, like we have some exchange and then we're done for the day. And then next week, I want to send a message to Zelda again. I do a new Diffie-Hellman to get a shared key, and then I send her a message and go back and forth. So every time I have something to send, I do a new Diffie-Hellman exchange. Another approach is to remember that forever. That if I want to communicate with you and I've never communicated with you before, I do a Diffie-Hellman key exchange to get a shared key with you, and then I store that key so I never need to do Diffie-Hellman again and use that key for all future communications. That's another approach that can be more efficient in some ways. Yeah. Yeah, what's the difference between the two? The primary difference between the two has to do with recovery from compromise. Okay? If someone hacks my machine, and I've stored the keys that I've used for communicating with everyone, they can download all those keys. So now they have the keys to decrypt all future messages I send. And if they were saving a ciphertext that I sent earlier, they can decrypt past messages too. Whereas if every time I want to communicate with someone, I first do a Diffie-Hellman key exchange, and then I don't store the key, the privacy impact of my machine getting hacked is a lot less. Someone who hacks my machine can observe any messages I'm sending right now, but not past stuff and not future stuff. So sometimes the most privacy sensitive applications will use this ephemeral stuff so that there's not a record kept that could later be used to reveal your communications. Okay, so if we look at the security of Diffie-Hellman. We said that this Diffie-Hellman key exchange is secure against an eavesdropper, Eve, who's observing passively what messages are sent between Alice and Bob. But it turns out it is not secure against Mallory, who generates fake messages or modifies the messages between them. Okay? So there's an attack, sometimes called a man-in-the-middle attack, where Mallory, let's say Mallory has compromised a router, and all messages between Alice and Bob are like being intercepted by Mallory, and Mallory's changing them and like deleting them and sending new ones and so on. So Mallory completely controls their network connection. When Alice is doing a Diffie-Hellman with Bob, she thinks it's with Bob. Mallory might be intercepting those messages and actually doing the Diffie-Hellman with Alice, so that Alice's messages don't reach Bob, they go to Mallory. And then at the end, you know, she sends stuff and Mallory sends stuff. And at the end, Alice ends up with this session key and Mallory ends up with the same session key. And meanwhile, Bob is sending stuff he thinks with Alice, but actually it's being intercepted by Mallory and he's doing this key exchange with Mallory. Mallory's running another copy of herself to interact with Bob. And they end up with a shared secret. And Bob thinks this shared secret is shared with Alice, but actually it's shared with Mallory. So Mallory ends up with one shared key for you talking to Alice and another shared key for talking to Bob. And then if Alice sends a message that she thinks is going to Bob with that shared key, it's with a key that actually Mallory knows. So now Mallory can decrypt that message. So Diffie-Hellman key exchange. If there's an eavesdropper who's passively observing messages but not modifying them or injecting fake messages, secure. But if there is an attacker who can modify messages or inject fake messages, not secure, because Alice has no way to verify who she's doing the exchange with. She can't tell the difference between doing the exchange with Bob or doing the exchange with Mallory. The way to verify that, to provide authentication, would be a message authentication code, but that requires a secret key. All right, so Diffie-Hellman is great if you believe that there's an attacker who's eavesdropping, but not injecting fake messages or modifying messages. But it's not enough if there might be an attacker who's also modifying messages, because of the man-in-the-middle attack. Okay, so that's the primary shortcoming of Diffie-Hellman. And another, and I guess kind of very closely related, maybe it's the same vulnerability in some sense, is it doesn't provide authentication. When Alice and Bob do Diffie-Hellman, Alice can't authenticate that it's Bob that she's talking to and shared the key with. She knows that she shared a key with someone, but she can't know who, because it could be actually Mallory who's pretending to be Bob who's sending these messages and receiving them. Okay, so we're sort of halfway there. We have a solution to the problem with symmetric key cryptography, the problem of sharing keys, that works as long as there's someone who's passively observing, but doesn't work if someone is actively messing with our messages. Okay, so we're halfway there. I'm going to stop here. And then in our next lecture, we'll figure out how to solve the other remaining half. Have a great week, everyone.